Greetings, Panthers. It's Dr. Augustine again, and we are going to take a look at a simulation of gases. And this is done by the folks at University of Colorado, PhET simulations. Hopefully you've seen them before. These are really excellent simulations. And this isn't going to work fantastic on the video because I can only sample once per second on the video, so it's going to be a little bit blocky. But if you Google PhET Colorado and you look for gas properties, you can actually run this simulation yourself and you'll get the same sort of information. So let's set this up first before I start showing you what's going on. First of all, we have a container of some sort. We have a pump, which we can pump in some gas molecules. I can put in a heavy molecule or a light molecule. I can measure the temperature. I can measure the pressure. It's all using PV equals nRT. We can control the size of the box if we want to. So this first one we're going to show. So I'm going to pump some gas molecules in, and if I click on this, this tells me how many particles I have. So I have 50 of the heavy particles, and I'm going to pump 50 light ones in there as well. And you can see how this impacts the temperature, see how it impacts the pressure, and if we adjust some variables, like for instance, if we adjust this, I can heat it up. You can see the temperature is increasing, the pressure is also increasing because of PV equals nRT. The molecules are also moving faster. Again, it may be a little bit difficult for you to see. That's just sort of a general PV equals nRT. You can adjust a bunch of things and you can hold things constant if you want. Right now, nothing is held constant, but if we held the temperature constant, we could do the individual gas laws. Okay, so this is gas properties. Now, let's take a look at the energy distribution. So I'm going to show the number of particles. I've got heavy particles and light particles. I'm going to pump in 48 heavy particles and 50 light particles. Let's bump up to 50 heavy particles. So I have the same number of particles, the same start that we had. And what I want you to call your attention to here is this is the speed distribution. This is number of particles versus speed. And if you recall in the last video, that's the Maxwell-Boltzmann distribution of speeds. And if you look at the average speeds, you can see that the heavy particles are moving about 3 times slower than the light particles. And that's because at a given temperature, there's a fixed temperature, 300 Kelvin, at a given temperature, light particles are going to move faster than heavier gas molecules. Now I'm going to adjust a few things. I'm going to turn some other functionality on. So I've just turned on a graph of the speed distribution of the red molecules and the blue ones. And you notice that I know it's a little bit blocky, and the reason why it's a little bit blocky is we have a set number of molecules, only 50. If we had 50,000, we'd have a nice smooth curve. And this would be that Maxwell-Boltzmann distribution. The thing you notice, though, is that the average, or the peak of this red curve, is at a higher average speed than the peak of the blue curve. So this is everything we already talked about before is being shown here. Only, again, it's not this nice smooth curve, and that has to do with the fact we only have a limited number of molecules. Down below, we have the kinetic energy of this system. And if we turn on the red and blue for that, if you look carefully, you notice they basically overlap one another. And that's because, remember, the kinetic energy is directly proportional to the temperature. Just because we have 2 different masses, they have basically the same kinetic energy. The small molecules are moving faster, but they weigh less. So the kinetic energy is still the same. So the red and blue lines basically map over top of one another as the kinetic energy. This green line is the total kinetic energy. So that's just the sum of those 2 things. Okay? So we're seeing the Maxwell-Boltzmann distribution at play in this simulation right here. Now, I'm going to add one more little twist to this, or I'm going to change the system just a little bit. I'm going to adjust this knob up top. And what I'm going to do is this is actually going to open up a little hole in the top. And that's going to simulate the phenomena of effusion. And what I want you to look at when I do that is I want you to look at the number of particles. Okay, so I'm going to open this hole up, and this is going to be like an effusion cell. An effusion cell is a container with gases that have a little pinhole in it, which allows some gas molecules to leak out. And I want you to look at 2 things. I want you to look at the number of gas molecules that are leaking out over time, and I also want you to look at the average speed and the temperature as we do this. And I'm actually going to change the temperature to Celsius because that's a little bit easier, just kind of more familiar with that. So let's drag this open just a little bit. And we'll watch as some molecules drift out. So far we have almost even numbers of the molecules drifting out. And what do you notice is happening to the temperature as we're allowing gas molecules to effuse out of the chamber? So one thing you notice is the temperature is slowly dropping. Okay, we start at 27 degrees C, we're down to 4 degrees C. So the temperature is dropping. Every time one of these hot molecules leaves, that's because of the motion, it's a hot molecule. And the other thing we're starting to notice is the light molecules are able to effuse more efficiently than the heavy molecules are. So this is actually the way that uranium was concentrated, or one of the ways that uranium was concentrated during the Manhattan Project. You had two different isotopes of uranium, uranium-235 and uranium-238. And by building an effusion cell, you could get the lighter uranium to effuse more efficiently than the heavier uranium, and then you can gradually concentrate. You can basically have another cell up here which collects the lighter ones, and then a series of these cells which allow you to gradually make a higher concentration of the lighter and lighter isotopes. You see now we started at 50, we're down to only 20 light ones and 36, or 19 light ones and 36 heavy ones. So we're actually concentrating the heavy gas here, and if we were to look at this chamber here, we'd be concentrating the light gas. If we had a whole series of these diffusion cells, we could gradually make the gases heavier, or we could concentrate the lighter gases increasingly. Now, fortunately for us, this is not an easy thing to do with uranium, or every crazy nation in the world would be making fissionable uranium to make nuclear weapons. But this is one of the ways that the Manhattan Project did this. Okay, so that is effusion. Now, let's stop and let's take a look at a similar phenomena called diffusion. So what I'm going to do here is I'm going to start out with a same number of gas molecules. I've got 40 particles in each side. I'm going to change the masses. So I'm going to do 32 on the blue ones. I'm going to make that oxygen. So what I have is two different gas molecules. I have one gas molecule with an atomic mass of 32. That's like oxygen. And then I have one that's 20. That's like neon. And I've got different atomic radii for each of these. They're both at the same temperature. I have 50 particles of each of these, and I have a divider separating these. So this is different from effusion. I've got two different gas chambers with this divider between them. So there's a couple of things I want to point out before I get this going. First thing is this bar down at the bottom. This is the center of mass. So if we were to take all the masses of each individual particle and calculate where it was relative to the x position, the line between the barrier and the edge, this would be the center of mass. The average mass is right where this line is, and of course the red one is here. And what you notice is these are basically in the center of the box. Now you can see it's moving some, and that's because there's a limited number of particles. If we had 10 million particles, this would be really close to the middle. If we had 10 to the 23 particles, this would basically be in the middle. It's drifting around slightly because of the motion of the particles, but it's basically staying in the middle. So what I'm going to show you then is I'm going to remove this barrier, and we're going to watch the molecules, the flow of the molecules from one location to the other. So I'm going to remove the divider now. And now if you keep an eye on the molecules, you can see that they're starting to slowly, the red ones are drifting this way, the blue ones are drifting this way. The center of mass is now moving towards the middle of the entire chamber. Eventually it will get towards the entire chamber. And this shows how many are on each side. We started with 50, so we should have roughly 25 particles on each side of the barrier, which is about what we have right now, 24, 25, 26. So this is the phenomenon known as diffusion, not effusion. So diffusion is if you have a high concentration gas in a certain region, and then you allow it to reach equilibrium. So now, at this point now, we are at equilibrium. We have basically an equivalent number of gas particles on each side of this, what this barrier used to be. This is the reason why if someone opens a bottle of perfume in a room and you're sitting across the room, eventually you would smell the perfume because it would have diffused across from the low concentration or the high concentration region, which is where the open bottle is, over to you, the low concentration region. Same thing if a skunk is in the, gets hit by a car or something, you would eventually smell that skunk from far away because the particles, the gas particles of the smell from the skunk would gradually reach your nose. Okay, so diffusion is a concentration-driven phenomena. There's a concentration gradient and a higher concentration at one point and gradually flows to a lower concentration until you reach equilibrium. Effusion is due to this pinhole effect, and as we mentioned, the lighter molecules effuse faster than the heavier molecules do. There are equations in the book for how to solve all this stuff. That I'm not going to hold you responsible for that. I just want you to understand the conceptual ideas behind these phenomena. And if you really want to take a look at this yourself, my recommendation is to go to the PhET simulations and play around with these yourself, to play with different parameters, and you can get a feel for what they're like. All right, that will do it. Thanks for watching, and our next video will be deviations from the ideal gas law.